Okay, I guess it's time to start. Oh, some people are still coming. So today we'll start talking about reinforcement learning, and we will do it for the next 3 lectures. So first of all, what exactly is reinforcement learning? We can look at some basic definitions. So Wikipedia says that reinforcement learning is concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward, which is probably pretty precise, but I'm not sure how familiar you are with all those terms and how you can imagine something tangible there. If you look at the book that I very recommend, and I'm actually building the lectures according to that book and the slides that come with that book from Rich Sutton. In this book, they say that it's reinforcement learning is learning what to do, how to map situations to actions, so as to maximize the numerical reward signal. And I'm kind of simplifying these long definitions to learning to choose actions to optimize rewards based on experience, trials and errors, right? So the big difference from the standard learning is you are in a standard learning, like supervised learning, mainly you are learning some patterns, right? How some inputs map to some outputs. But you have examples of inputs and outputs, right? If you have a handwritten picture of a digit 4, the output is the digit 4, right? And you have plenty of examples of inputs and outputs, how to create this mapping. In reinforcement learning, you, instead of creating some mapping, you are choosing mainly actions. And the only information, what actions to choose is the reward. So if you choose the right actions, on average, usually, not always, you get high rewards. If you choose bad actions, you get lower rewards. Right, so it's all about actions and rewards. At the beginning, I would like to show you a couple of examples where reinforcement learning has been very, very successful in the past decade or so, or 2 decades already. And you have probably heard about all the successes mainly DeepMind had in games, right? So they made an agent which was able to play any Atari game. Like, doesn't sound that impressive, but we'll get to that in a separate lecture when we will be talking about this particular agent. But it was the very first system which was very general, right? Like before that, if you had a system to play chess, it could play chess and nothing else. If you had a different system that was trying to do machine translation, it was doing machine translation, it couldn't do anything else, right? And this was the first system that could play, like the same system, could learn to play any of the Atari games, right? That they had a whole battery of, I don't know, over 50 different games, which were from like playing tennis to boxing to these arcade games to moving and exploring some environments, and so like very, very different kinds of tasks. And the agent didn't know anything else, just like saw the screen and knew the score, like am I doing well or am I doing not well? And it was able to learn to perform like in a superhuman way on these. But also there were a lot of successes in specific games in which, thanks to reinforcement learning, we were able to find superhuman strategies. So if you think about chess, about Go, about anything like that, if you try to encode all the human knowledge that people have, you are always somehow limited, right? If you learn from what people played in the past, you can very hardly play better than the best human ever, right? Because you are always just learning from the mass of humans, and you have not seen enough data from the best people, so you have to use some of the worst people as well, and that's why you will be always limited. But once you use reinforcement learning, you don't tell it at all how to play, what to do. You just tell it, these are the rules. Now figure out what to do, play with it, like try different things, and through trial and error, learn to play as well as you can, like generally against itself. Then you can come up with truly superhuman bots, right? Then you are not limited by this human knowledge you are trying to learn from, you are trying to encode into the system. Does it make sense? Another similar domain where you can see this pattern, where like it's just impossible to encode all the human knowledge, is in robotics. So if you take, in general, simulated robotics,
Připojte si zdarma ke svému tarifu třeba ta...
and you take some kind of a humanoid or whatever robot, you give it into a physics simulator, and you just, at the beginning, you let it to move randomly. And then you reward it if it stays standing, for example, or if it moves ahead enough. That's a very simple reward signal you can give it. And then if you give it a lot of time, a lot of compute, it will try all sorts of movements, and it will learn which worked, which didn't work. And eventually, like after many, many iterations, it will learn to run, like in a funny way, maybe, but in an efficient way. And if you train it well, if you look at some like better trained models, so this is a famous paper from DeepMind where they had different types of robots, like it doesn't even matter, right? You can build anything that could potentially move, and then you can train it, and here you will reward it for like getting as far as possible, and you don't tell it anything else about how to move, right? It's like a child. Like when a child is born, it doesn't, like you don't encode into its brain what to do. It tries, it explores, and whenever something works, it will try doing it more often, and eventually it will learn to be very proficient and in many things that it's trying to do more often. Right, so this was not told anything about how to move. This was just given its shape, move, like ability to move, some actions, like you can change this angle, or you can move this like there, and then it learned on its own. And these are all in simulation. And once you deploy it on an actual hardware, usually these things are trained, like you train it in simulation a lot because you need a lot of data, and then you try to deploy it, and maybe you train it a little on the real one. And if you think about the movements, like it looks super natural, and if you imagine there is a little eyes there, that you would program these movements of the legs, right? If it's pushed, this is big dog, this is Boston Dynamics big dog. Like you could never anticipate all positions where the dog could be and how it should move the joint and actually program it, right? So this is also trained by reinforcement learning. Okay, another big application is advertisements. When you go to a web page, you usually see here some ad, for example, here for teplaki. And what you see, what kind of ad you will see, usually depends, like the site that is showing it is paid for whether you click on it or not, right? So it doesn't make sense for them to show you something you wouldn't even click on, right? So now they know that you are coming, and they have a couple of things. They can show you teplaki, they can show you a concert, they can show you some new gadget, like a new mobile phone or something like that. And now they want to decide what to show you, right? And they don't know initially, right? So they start exploring, right? They show a couple of people this thing, they show a couple of people that thing, and if something works better, they'll show it more and more often. And this is like the basic principle behind advertisements still, like to this date, with some caveat I'll talk about later if you don't ask meanwhile. But you also use reinforcement learning to learn about this. And then eventually, now the huge boom of language models. Language models are trained in several stages. Like first stage is just consuming the internet. That is the stage which people are most talking about. But then it is not very helpful. Like when you train it, it will able to predict the next word, but it will not able to follow instructions, right? Like if you tell it to write your homework, it will not maybe write your homework, and that's why it will be not that helpful, because you need to somehow encode the instruction following, like what is better behavior and what is worse behavior. And it's very hard to do, right? Like to hand code rules like, okay, I want the language model to give these answers in these situations, that answers is then that situations. It's so general system, and people are using it for millions of different things that like consistently writing some rules how to be, or program how to behave well is impossible. And that's why from very beginning, from ChatGPT, people were using reinforcement learning to fine-tune the models to do what they want, right? So they always generated like two possible answers because it's a stochastic model, so you can generate two different answers, and then they ask a human, like, which of them do you like more? And they say, okay, I like this one. And then they generate another two answers and ask which of these two is better, and so that one. So from this simple feedback of preference between two outputs, they create a preference model and trained it using reinforcement learning from just this feedback, like this is better or that is better, right? In such a complex setup as language modeling. Questions? No questions, everything is clear. Okay. So that's kind of a practical reason why reinforcement learning is a good idea, but there is also a more fundamental reason. Like I mentioned it briefly, but if you want to study intelligence, really like how our brains are learning all the fabulous things that they have learned. Like they were not programmed, like nobody was injecting any knowledge into our brain directly. The only thing we had was our eyes, our ears, our sensors, so we were like observing the world, and then some feedback, like right, pat on the back, like this was good, you are doing well. When the kid is trying to walk, right, it doesn't have any direct knowledge. It has just some reinforcement from the parents, like yeah, this is good. Probably don't try to hit your head too hard on the wall or on the floor. That's bad. And even your body like gives you this feedback, like this hurts. This is like fun. And just based on this very little feedback, you learn everything. Like you learn all the intelligence you have, right? So if this is true in us, then probably we can replicate a similar systems in computers and achieve artificial intelligence in this fundamental way only by observing the world and getting very minimal rewards about like what is good to do and what is bad to do, right? And this is like so fascinating that people are studying it for a long time, even though reinforcement learning didn't work. Like it started in 60s and it was never usable for anything practical for like 40 years at least. And people were still studying it because of these fundamental reasons, and they are exploring the connection with neuroscience and so on. So, to sum it up, you can view reinforcement learning as a more autonomous learning, right? Learning from just the reward, not directly some examples of inputs and outputs. And all reinforcement learning like books and courses and many papers will have this picture, which is kind of the most fundamental straight to the bones model of how reinforcement learning works. So you have an agent. The agent is able to perform actions in the world. As a result of those actions, the world gives some sensations, some states, some sensory inputs, and some special input that is called reward, that the agent knows that it should maximize this or minimize some penalty. So it requires less input from people. It's super easy to program because if you have a robot that is learning, you can really just like give it thumbs up or thumbs down based on what it's doing, and it can learn from that. Okay, questions? So this is how you view it, but if you think about it, like how to model the world, how to model this part, then we are coming back to our favorites, Markov decision processes, right? So it might seem as something formal, but you have seen many examples how you can model like real-world examples in this formalism, and that's why we were pushing in this course why formalisms are important, because any real-world problem you can model in this MDP framework, then you can use reinforcement learning, because all the algorithms for reinforcement learning are formulated on MDPs. they are studied, like if you want to prove some theoretical properties, like how quickly it will converge, whether it will converge, or, and so on. It's all done on the MDP model, right? That's the most fundamental model of reinforcement learning. Like then you have the complications of POM-DP and whatever, but MDP is the most fundamental model. So you have a set of states, some rewards, actions, discrete steps of time, generally not necessary. Like you can have reinforcement learning in continuous time, but it's a little more complicated. We'll be not dealing with it here. And environment dynamics, which is the probability distribution of the next state and reward given that you perform some action A in state S. And then you have the Markov property, right? That's why it's called Markov decision processes, that you know that everything that is happening in the future depends only on the current state, right? That's the Markov property. You don't need to remember the history. The history will not influence anything. Like all the relevant information from the history is somehow compressed into the current state of the world. Doesn't need to be the current observation, like then you have the POM-DPs and so on, but the Markov property says that the state of the world is all you need to know to like develop it further through the actions. Okay, so what does it mean? You already had the examples, but if we go back to the Atari games, for example, then the states will be what you see on the screen, pretty much. Like that's not completely Markovian, so these assumptions are sometimes not perfectly obeyed, but still it's a very useful formalism to think about it. If you take a couple of frames, what they do after each other, then it's much more Markovian because you can have more information in it. Rewards is the score in the game. Actions is the movements of the joystick, right? And the environment dynamics is actually the game engine. Like what happens if I make this action, if I move the joystick this way in the game, then this probability distribution is realized by the program of the Atari machine. Questions? How would it look like in robotics? If you have a simple robot, what is a state? Yeah, definitely. Like angle of each joint will be one part of the state, and then potentially like it's a part of environment, right? So the position of the robot in some kind of a maze or something can be also the part of the state. The rewards could be, for example, like if you are like a Roomba, your reward can be like every time you come to a new part of the room where you have not been before, right? You are vacuuming, then that's your reward. For every kind of new position you get a point. And then the actions would be like you can turn around or you can go forward, right? So you can really model almost anything using these MDPs. But for this lecture, we will simplify things a little bit, and we will be dealing for the most of the lecture with this super simple MDP in which you have just one state. You have one state. In this state you have several actions, 1 to n. Each action will give you some reward and then return you back to the same state. So it's super simple, the simplest MDP you can imagine, right? Just one state. But still, it's already very fundamental for reinforcement learning. You can study the basic properties of algorithms, basic like questions that you need to answer. Just understand the problem on this simple model, and then in the next lectures we'll expand it to the full MDPs. But for now, it will be enough to think about this model. Does everyone understand it? Because we will be talking about that for the rest of the lecture, pretty much. Okay, so you can see in the title that is also called multi-armed bandit problem. Why is it called multi-armed bandit problem? Because of this kind of motivational example. that you are in a casino. This is called one-armed bandit in casinos, and you know how it works. You will take a coin, you will drop a coin, you will pull the lever, and then something will be happening, not that important, and then either gives you a reward or it doesn't give you a reward. Most of the time, it doesn't give you anything, right? Sometimes it gives you a small prize, small winning. Sometimes it gives you a jackpot, a lot of money, right? But most of the time, it doesn't give you anything. The feedback is very, very delayed. And now the question is, if you know that they are not all the same, if you know that some of them give you more reward, some of them give you less reward, right? Some of them give you a little reward very often, some of them give you not that much reward, not that often, but huge reward, right, every now and then. And now you have a bucket of money, right? You are the old lady with the bucket of quarters in the casino, and you have to like throw the bucket somewhere into these machines, right? So how do you do it? You want to maximize your winnings, of course. You don't know anything about the machines, only that they are not the same. Like each of them is different, and you have this like 1,000 coins, and you want to throw 1,000 coins into the machines, and you want to win as much as you can. Any ideas? How would you start? Like, what would you do? Yeah, you can sample it randomly. Like you can just evenly split all the money, but then, like, yeah, you will get some reward from each of them. But what if one of them is giving you way more than the others? Then you will waste all the remaining 3 piles, like 3/4 of all the coins, right? If there is just one that gives you something, right, and all the other just don't give you anything at all, then you will waste 3/4, right? So just randomly throwing to everyone, like it's a good start, definitely, but it's probably not the optimal strategy. So how can you improve it? Exactly, right? So you can somehow try to estimate the quality, the reward of the machines in time, use some amount of money initially to find out, to explore, like which machine is what quality, and then once you are sufficiently certain, you will put the rest of the money to the one that seems the best, right? And you will exploit the knowledge you have to maximize the reward, right? And this is the fundamental trade-off that bandits are used to study, like this trade-off between exploration and exploitation, because like how much you want to explore and how much you want to exploit, right? Do you want to put 10% for exploration and then exploit, or do you want to do something smarter? And in general, you can. So first of all, the assumption of the multi-arm bandit problem is that there is an underlying reward distribution behind each of that arms, right? Like each of the machines behaves consistently in time for now based on some probability distribution, right? So the first machine can give you always 8. That's nice. The next machine can give you, with 80% chance, it will not give you nothing, and with 12% chance, it will give you 100. Next machine will give you uniformly any sum between -10 and +35. Like it can be negative in general. Like doesn't matter. And the last action can give you with in third of the cases nothing, in third of the cases 20, and a third of the cases like a uniform over something. Like it doesn't really matter. It can be any distribution at all. The only requirement is that it's consistent in time. So which of those actions would you choose? So let's refresh the statistics. So how are you choosing them? Based on expected reward, right? So you need to compute the expectation. The rational agent would take the one that has the highest expectation. The expectation of first one is 8. The expectation of the second one is 12. The expectation of the next one is a little more difficult to compute, but it's 1.5, and the expectation of the last one is 11, right? So out of these, you should eventually, like if you have infinite number of coins, you should eventually throw them into action 3, right? But if you have a finite number of coins, then you need to somehow balance the exploration and exploitation to get the most on the way. Is the motivation clear, or anything is unclear or missing? So this multi-arm bandit problem, if you define it formally, it's a set of time steps. That's the size of the bucket of the money you have. Set of actions, k different actions, and then the real valued reward. You expect that the reward is only dependent on the actions and it's identically independently distributed. This is that it's independent draws from the same distribution, that it doesn't depend on history or anything. That's the Markov property. And then you have some Q star, which is the expectation. But you don't know these true values, you don't know this distribution, and you still want to maximize your reward, so you want to do the trade-off between exploration and exploitation. Just some terminology. If you have some kind of estimate, so this notation is taken again from the book. Always the capital letters are random variables. So this means Q are usually estimates of action values. At time t, value of action A. And this Q star is the optimal, the expected value of that action. So this is the random realization of the samples of our estimates. And this is the reality. So let's assume that at some point t, we have these estimates for each action. Then we say that we are taking the greedy action, the one that is exploiting our knowledge so far, if we are taking the one that looks the best so far, right? So that has the highest estimate at time t. And whenever we take some other action, we say that we are exploring, because based on the knowledge we have so far, we expect that this action is not the best, but because we know that our knowledge is limited, we want to explore it more. We want to be more sure that the action is not the best, and that's why we are exploring. And of course, like based on this formula, you see, you cannot do both at once. You have to either explore or all exploit, and you want to balance this in the right proportions so that you optimize your reward, right? So that's another important thing in reinforcement learning. It's not always true, but reinforcement learning, people like to say that it's learning at the same time as executing, right? So in supervised learning, you have the training phase, when you can do whatever, nothing costs you anything. And then you have the test time, when you actually use your model, and you care about your reward only at that time. In reinforcement learning, very often you have the setting of like lifelong learning, where you have the agent in the environment, and you would like the agent to improve while doing well already, right? So with showing the ads, you don't want to show random ads for 5 days until the campaign is over, and then you know which one is the best, but you didn't make any money, right? You really want to make the money at the same time as you are exploring and improving. Okay, so as your colleague already said, the simplest way to do it is to try to estimate the value of each action, and it's called action value methods. And you can estimate it using an average, right? So for each action, your QT, the estimate of the current quality of that action, will be sum of rewards taken prior to time t, divided by number of times the action A was taken prior to t. And the book, and this is a common notation, when I write 1 with some condition, that means that this is 1 when the condition is satisfied and 0 when it's not satisfied, right? So it's really just a notation for the average. And you know from the law of large numbers that if you have infinite number of trials, then this will converge to the actual value. And we will use this n to denote the number of times the action n has been taken. So up until time t, the action A has been taken this nta times. Okay, so now we have the estimates of the action value, and we can define our first algorithm for like balancing this exploration and exploitation, which is rather simple, and it's called epsilon greedy action selection. And it's just choosing the greedy action most of the time, but with probability epsilon, it will just choose a random one. And for now, the epsilon is just a constant. It's just a definition. So just to refresh the notation again, so you will have these queues which will store the estimates of the values, the n's which will store the number of trials you already used for that action. And then you will repeat every time you will take the greedy action with probability 1 minus epsilon, breaking ties randomly. So if you have two actions which have exactly the same quality, you will pick a random one. And then you will pick any action, including possibly the greedy action, like any random action with probability epsilon. Then you will call the environment. This bandit A is just calling the environment with action A. You will get the reward. And then you will update the number of trials you used for this n, and you will update the queue using this kind of strange update. Who knows what that is? What does it do? It's average. Who sees it? Who thinks it's obvious that it's average? One. Great. So in a while I'll show you why it's average. But yes, this is just a special way of computing average, which is quite fundamental for reinforcement learning, and you will see why in a minute. But first, let's see how it works. So you will be using this in the lab as well, and just to evaluate, the book is using this as well to like explain and show bandits. It's called 10-armed testbed, and it's just a synthetic environment where you have these 10 actions, where each action is chosen. First, you choose a mean, like the expected value of the action from a normal distribution. Does everyone know what is a normal distribution or Gaussian distribution? Who knows what is a Gaussian distribution or normal distribution? Everyone, almost everyone. Okay, so it's the standard like bell curve, right, where you have high probability of picking things somewhere around 0. Here, this is the mean, and this is the standard deviation, and this is the width, right? So you have denser probability around 0 and with 1. So you will first pick the center, and then you will pick the rewards based on that center with unit variance, right? So it's written on this. This is one realization of that environment. So every time you initialize the environment with different city, you will have a different environment. And the environment here, like this is the real value that you don't know of the first action. This is the real value you don't know of the second action. And this represents kind of the samples, the distribution. If you will be sampling, like choosing action 1, you will always get a sample from this distribution. If you choose some action 6, you will get a sample from this distribution, right? And then for the results I'll be showing on the next slide, you will run this for 1,000 steps. That's your bucket size, and repeat the whole thing 2,000 times, because it's all stochastic and kind of random, and you want to smooth it out. And this is what you will get. So if you take the epsilon greedy and you set the epsilon to 0, you will get 1. And you will not be improving much, right? Because what do? You are always taking the greedy action. So since you've initialized the queue to zeros, like if you get anything higher than 0, you will just stick to that action and you will play it forever. Yes? Mm-hmm. Definitely. This, yeah, thank you very much for the question. Like that's the normal distribution. That this is normal distribution with the center of 0 and variance of 1. And this is the normal distribution with the center of QA, like the previous samples thing, and the standard deviation of 1. Yeah? Yeah, that's perfect. Like ask, that's why we are here, right? Like otherwise you can just play a YouTube video. Was there another question? No. Okay. So this is what's happening. If you just pick epsilon 0, then you will stick to the first action that looks at least a little reasonable, and you will do it forever, right? If you take epsilon 0.1, which is like 10% of the cases you are exploring, you will get some reward. And you will get, like, you will not be improving much anymore because, like, you already find which is the best one, and you are still wasting 10% of your effort for the exploration. But you are quite good. When you have epsilon 1%, then you are growing much more slowly, right? Because if you find an action which looks good so far, you will be picking it very often. And just 1% of exploration is not much to find the action which just randomly was not as good as it should be, to find out that it actually is very good, right? You would need to have a lot of samples there to find out if you just were unlucky for a couple of trials. So how does this continue? Here. Who thinks that the red one will go above the black one? Who thinks that the black one will stay above the red one and the red one will go to the black one? Okay, why one or the other? So how does it look like in the infinity? Exactly. So the red one would be choosing the maximal action, the optimal action, the maximal one that is possible 99% of the time. And the black one? 90% of the time, right? And the rest they will pick randomly, so they will pick some worse one. So eventually in the limit, the red one will be above the black one, right? But this is also important in the exploration versus exploitation dilemma, that if you have just a limited time, you very often want to over-explore because you don't mind that eventually you will be losing something. You want to find a good action quickly. So all the theory also takes this span into account. Like if you want to make sure that you are optimal, you need to know what is the T, what is the number of trials you will have to balance the exploration and exploitation the right way. So here is a different view where there is how often we are picking the optimal action, right? So the greedy epsilon equals to 0 is picking the optimal action in like 1/4 of the cases, roughly, right? Because there are it looks like 1/3 of the cases. If there are 10 actions, and we take one sample from each, yeah, like the maximal distributions are quite tricky how they behave, but this is what happens, right? So the probability that we will hit by this completely greedy way the optimal action, like there is some chance, right? Like we can always just be lucky and find it, and this happens in 33% of cases. If we have the high exploration, then we are rather quickly converging to it, but then we are using it less and less, and as your colleague said, like eventually this would level up to 90%, and this would go slowly up to the 100, like 99%. Okay, is this clear? Like this is the first algorithm that is basically doing reinforcement learning, right? It's doing trials and errors. It is eventually guaranteed to play optimally. It's not guaranteed to like find it as quickly as it could, but like epsilon optimally, not really optimally, but up until that epsilon. If you reduce the epsilon in time in the right way, then you can even guarantee that you will converge to the optimum, right? But you have to like be sure that you are reducing it slowly enough to not mess things up. Is this clear, or are there any questions to this algorithm? Okay, so let's get back to the averaging. So to simplify notation, we will forget about the action A, right? Like now we will just assume that we have just one action, and we want to estimate its quality, right? So we will take the rewards for that action and divide it by the number of times we have used that action. And we want to compute it incrementally. We don't want to store the things. And of course, like we could store the sum and the count, but that is not as useful as using this incremental update, because this is kind of very fundamental way how to think about learning from experience. Because you have some estimate, some original estimate of a value, and then you have the error of the estimate with respect to your current observation. So you believe that it's good, like 0.9 good, and now you find out your reward is 1. So your error on your expectation, your surprise, kind of, is that, yeah, that it was 1. It wasn't just 0.9, right? So this is your error, and you add the error you had with some kind of weight to your original estimate, right? So it's really fundamental way how everything is learning. Like you are always kind of estimating how things will go. If they go as you expect, you don't change your estimate, that's fine, right? But if the things go very differently from what you expect, then you want to update towards that thing that happened, right? You will think that, okay, something will be happening more often, something will be happening less often. Every time when your expectation is not matching what is happening, you want to update it a lot towards that side, right? So this is a fundamental kind of learning rule where you have old estimate, step size, the target, that's the new information you learned minus the old estimate, right? And that's what you are doing here. And if you want to see that it's the average, it's just a simple algebra. So the Q is 1 over n and the sum of the rewards, right? Then the sum of the rewards, you will take out the first or the last reward and leave the rest of the rewards intact. Then you will multiply it by 1, right? It's n minus 1 over n minus 1. You will look at this, right? This is the same thing as this, just at Qn. So you replace this formula by Qn. And then you multiply this by this. So you have Qn minus Qn, and then you just rearrange it. You take this out, you cancel it with this 1 over n, and this 1 over n with this, and this will stay. Right? So it's nice to say that, or see that if you take 1 over n as the step size, so the amount of how much you update if your expectation doesn't match decreases with time as 1 over n, then you are exactly computing the average. And now, like in the whole stochastic optimization and learning and everything, depending on how you compute this error, because this doesn't need to be just the simple error, and what is your schedule of the step sizes, you can have different optimization algorithms that will converge to different kinds of like means, not just the actual average. And that's what's very often used in reinforcement learning, that you always have this kind of error notion, but then you have possibly some different schedule of the weights, how much you take into account the change that has happened. And this is just for the information that if you have certain properties of this schedule of the size of the updates, then you have certain guarantees. So there is a lot of theory in reinforcement learning, like trying to understand these things very, very precisely. So if the sum of the weights of the updates is infinite, but the sum of squares of the weights is finite, then it is guaranteed to converge and to converge at an optimal rate. Like it can converge to slightly different things possibly, but it will converge. And very often, like, these are not debates. So again, these are to understand where you have some properties, but doesn't mean that you cannot use different schedule. And very often in reinforcement learning, even the constant is used as a schedule, right? So you can really just take a constant step in that change, and it's useful when the IID assumption is not satisfied. There is more about it in the book, but I'll not go too deep into it today. So you can have different schedules; they can have different properties. Okay, so that was epsilon greedy. That's one algorithm for bandits. There are, of course, other algorithms with other properties. And one is called optimistic initialization or optimistic initial values. So I would show you the algorithm again and point out that here we set the Q to 0. And I want you to think about what happens if we don't. What happens with the algorithm if we set the Q to something else than 0? And for simplicity, you can think of epsilon equals 0 as well. What is the impact of that Q on exploration? Yep. Yes, so if we initialize something really badly, right? If we initialize it to -10, we'll never try it. That's a good point. Any other observation? Yep. Mm-hmm. Mm-hmm. Yes, so it's a similar point. Like if we initialize all of them low, then the very first one is probably be the one that will be taking forever, right? So mm-hmm. Yes, definitely. So if we guess it right, the initialization, then we can converge more quickly because we can insert domain knowledge this way. That's a good point. What if we use the optimistic values? What if we overestimate it? We start with a Q higher, much higher than what's supposed to be there. What will be happening? Exactly. Yeah, that's a very good observation. Yes, that's true. Like, it doesn't really matter. Like, if we choose optimistically, then the effect of the Q1, the initialization, will like diminish eventually. But it will still have some effect on how we converge, and it will strongly encourage exploration, right? If we initialize all of them very high, we will just say, okay, even if this action doesn't look so good, just try it one more time. Try a couple more times than you would otherwise, and you will explore. You will like motivate exploration this way, right? So you can see it like this. If you add the Q1 to the average, of course the Q1 is divided by n, so eventually this goes to 0. So it doesn't really, if you are choosing the action, it doesn't really matter. But and eventually you are getting the right number. And that's, again, a super fundamental principle in reinforcement learning, which is called optimism in the face of uncertainty, which is a trivial thing, but it's good to realize that if you are like too optimistic without any reason, you will find out, right? So if you are over investing to something, over exploring, then you will find out that you were over exploring, and in the time you can forget about it and not do it anymore. If you are under exploring, if you are pessimistic, you will just not explore sufficiently some part of the space, and you will never find out that that part of the space is actually good, right? So this basic principle, like optimism in the face of uncertainty, if you are doing some uncertain decisions, like being optimistic is always good, because that will help you find out when you are wrong. Being pessimistic will not allow you to do that, and you will never explore enough of these actions, right? So that's even like a life lesson, not just a reinforcement learning lesson. And here is how it works. So again, the same 10 armed bandits setting, and now you take Q1, the initialization to 5. You know that the values are usually around like 1, 2 tops, and now 5 is like twice as much. Like initially, it's quite bad because it's like using the optimistic bias, but very quickly it will find out the good actions, and eventually, would it converge to the right, to the optimal action or not? How do you know? Like we agree that if you take the action infinite number of times, it will find the correct value. But now we have several actions, right? And we are again still taking the greedy one. We just optimistically initialized it. So are we guaranteed to eventually converge to the right one? But it's not that obvious to see, right? If you think about it, this is some y-axis, right? So here you have some action which will have value 1.2, and here you have action that has value 1. And let's say that the time goes both ways. This is just every time you take this action, time goes this way, and every time you take this action, time goes this way, right? And you know that this is the average, but you are taking like a random samples. You are getting random samples from that. So if your estimate, your Q, capital Q, will be somewhere in this range with time, right? Here, it will be somewhere in this range, because it's a random variable, right? So every time you sample it, you will get some different values. You will be moving somewhere. What is this range, right? These are confidence intervals, right? Pretty much. And the confidence intervals converge to something like 1 over square root of t, right? If you remember, it's mean plus minus some z sigma square root of n, right? Something like that is the confidence interval formula. How quickly does the optimism wear off? Oh, 1 over t, right? So the optimism will overestimate it first, but then it will go below it. So this is just kind of intuition. It's not a formal proof because like probably nobody would enjoy it if I was making the formal proof here. But intuitively, the optimism will wear off more quickly than the stochasticity that is coming from the samples. So in this part, we can still overestimate it. We can still like take the bad action, which is just randomly, because here the worst action will be just randomly here, and the better action will be just randomly here, right? And we can still pick this action from now on. So this magic was just to motivate a little bit. So, okay, maybe, is there a better way? Is there a way how we can guarantee that we will converge to the right thing? The realistic initialization. But then we have the epsilon, right? Then we are still wasting the epsilon samples to the suboptimal actions. So the question is, can we eventually converge to the optimal action played like almost always in the mathematical sense, almost always, like that the expected value of what we are doing will be actually the optimal action. And we'll be exploring just enough like in this zero size set where we'll not be losing any reward. Yep. Yeah, like 1 over n, this is this, right? Like 1 over n is the effect of the optimistic initialization. We need something more, right? So we actually need to match the confidence interval, right? And that's the UCB, like the kind of ultimate bandit algorithm, which is pretty much computing the confidence intervals and always picking the action which has higher upper confidence bounds. So every time you compute your average and you compute your confidence interval, and the one with higher confidence is the one that is chosen. And the formula looks like this. So that's just the Q, that's the current estimate of the value, plus this is called UCB bonus. And that's kind of the bonus that if you are not choosing the action A, the time still goes. So this will grow a little bit. If you are choosing action A, this goes down quite quickly. And this balances the exploration and exploitation in like provably almost optimal way. So this bonus will actually go to 0 eventually. So eventually you will be deciding based on the actual values, but it goes slowly enough that you will never miss it. And I wanted to show you a demo on the next slide, but this demo doesn't work. I really like this demo. There was some random guy on the internet. So I had to program a simple replacement. So here it's 4 different actions in the UCB setting, right? This is initially all of them are 0. And I didn't want to run it. I want to stop it. No. Sorry about that. Okay. So first, you take first action. Like initially, this bonus, the UCB bonus, since you divide by 0 is infinite, so you need to pick every action at least once. So you will pick first action, you will pick second action, you will pick third action, you will pick fourth action, and you will get some kind of reward for each action. And then you use the formula to compute the confidence intervals. And then you are picking based on the upper confidence bound. So now this is the highest. That's again implementation of the optimism in phase of uncertainty. So, okay, if I was really lucky, like this is the best action, right? This is the optimistic decision on that best action, so I'll take this action. But by taking that action, I get more information. I reduce the confidence interval. I improve the average, right? And now, okay, this one seems that it could be the best one. So I pick this one. And then, yeah, this could be the best one. And now this could be the best one, right? And every time you take the one which has the highest upper confidence interval and you adjust that one. And you can see that all of the others the confidence intervals go a little bit up every time. And that's the logarithm t in the denominator, like in the denominator, right? So every time all of them go up a little bit, and the one that is chosen goes down a lot. And gradually you are just narrowing the intervals. And you are allocating the samples kind of really provably near optimally up to some logarithmic factor to those arms. One thing that I didn't talk about is this C. So what is the role of that C? What does it do? Speed how fast we want to converge. To some extent, yes. It's the amount of exploration we want. If we put larger C, we want to prefer exploration, so we want to put more weight on the exploration bonus. If we put low C, we are playing more greedily. If the C is higher than, like in theory, if you have bounded rewards from 0, 1, it should be something like square root of 2 to make sure that you will converge. Very often in practice, people are using smaller C. So because exploring right, making sure that you didn't miss anything, any optimal option, is very expensive. And in practical scenarios, you don't have enough time to make sure of that. If you put less, smaller exploration constant, you are exploring kind of roughly, and you over-focus on potentially suboptimal action, but the action is still reasonable. Based on the C, you can guess like how much suboptimal it may be. But very often in practice, you want to put lower C. In theory, you want to put higher C because then you have the guarantees, right? So that's the exploration that is somehow like often empirically tuned for different scenarios based on how much stochasticity they have and how much difference in different actions. Like if the optimal and second best actions are very close to each other, then it's very different than when they are very far from each other. Okay, so that's UCB. Any question to that? So here we have a comparison of average reward over first 1,000 steps in that 10-arm bandit scenario, depending on some parameters, right? Each of those methods have a parameter. Like the optimistic initialization has the Q0 or Q1. The epsilon greedy has the epsilon. The UCB has the C parameter. And I was not talking about gradient bandits. You can read about him in the book if you are interested. But that has an parameter alpha. And for different values of this parameter, it will perform differently, right? So UCB, as I said, like here it looks like it's around value 1, between 1/2 and 1. It's the optimal performance in this particular domain. The epsilon greedy with epsilon like 1/16 is the best, and the optimistic initialization, if you still have the alpha, if you still have the, I think this alpha is the epsilon actually, and it's taken from the book. Then the initialization just above 1 seems to be the best in this domain. Okay, questions to these bandits? If not, then let's go back to the advertisements motivation. So what would you do now? If you have a web page, you want to show ads, you are paid for how people are clicking on them, and you can show an ad for a concert, for a book, for a movie, for a vacation, for like some categories of things. So how would you do it? Would this lecture help you at all? Mm-hmm. Yep, like that might work if you are a Facebook and you are holding the user for like many displays, right? But if you are an ad network, if you are like on a Cessnam or somewhere, like you very often don't have the user logged in, right? So if you have like couple of displays for each user, then you would have to do something different. But this is like a very good way where we will go there eventually. But first, let's think about the user who is not logged in. Exactly, right? So every ad or every category of ad will be a separate arm of that multi-arm bandit problem. Every time a new user comes, you will, like using UCB or any of these algorithms, you will pick like which ad to show them. You will see whether they clicked or didn't click. If they clicked, you have the positive reward of +1. If they didn't click, you have the reward of 0. And the next user is the next time step, right? Over the same set of slot machines. Okay, but as your colleague very well pointed out, like the advertising networks are trying to force you all the cookies and everything to find out as much as they can about you, and they do it for a reason. So let's say that they can find out from cookies and stuff like a couple of other things, like your age, like number of your Facebook friends, and your gender, let's say. So they don't know you, like your identity. That's like privacy violation. They shouldn't have that. But maybe they kind of tracked you over other sites, and they have some estimate from your like browsing history or whatever, like what you like, who you are. So what do you do now? Mm-hmm. Perfect. Yes. So the point is that you would expect that similar users will have similar preferences, right? So you want to somehow group them into into groups of similar users and have like one bandit per this group. And the setting is actually called contextual bandit problem, which extends the multi-arm bandit problem with a context vector. It says that every time when there is a new time step, the new time step has some kind of characterization, some kind of vector of context. In this case, it's a new user comes to the page, and based on the cookies, we know something, some information about them. And we can have some data from the previous users, right? So let's say that we track separately which users we show a book at and which users we show a concert at. And now if we have somebody who is, I don't know, in there, I can draw potentially. Somebody in there. 30s, right? With, I don't know, 200 friends. We showed them a book ad and they clicked, right? Then we have somebody else who is like 35 and has 300 friends. We showed them a book and they didn't click. And similarly, like we have somebody who is like 40, has 80 friends, we showed them a concert and he clicked, right? And then we had another person who was 38 and had 90 friends and didn't click on the concert, right? So these are the data we have. And one option that the colleague was saying, okay, so let's somehow like cluster it so we can make some clustering of the space, and then we can run a separate bandit in each of those regions, right? So in this region we have one bandit, in this region we have another bandit. If we do it this way, like again, I'm not talking much about machine learning here because you have a separate course, but the way how to fragment this space to these like can be used, like can be done by decision trees, for example. So you can use machine learning methods to find like what this similarity means. You can use even simpler technique. Yeah. Mm-hmm. Okay, so if I understand correctly, like you say that, okay, there is a new guy here, I don't know, here. Is the same here. You can take some kind of neighborhood of that guy, right? Mm-hmm. You could do it. You could do it. You could update it this way, but then you have to do your own math to make sure that you are balancing the exploration and exploitation with all your weights and everything correctly. Like, it certainly is possible to do it that way, but I think it's much more complicated than, for example, what I'm showing now, where you take the new person, you take some fixed size neighborhood, and then you can really use the theory as you have it, right? So how many, then you have two actions, and you can compute what is the average value. So here the average value of this action is almost 1, right? 1, 2, 3, 4, 5, 6, 7, 8. So it's 7/8 is the average value. Here the average value of that person would be 1, 2, 3, 4, 1, 2, 3, 4, 5. So that would be 4/9, right? So you can use the same you can use the same UCB formula that we know a lot about to allocate it, right? If you take some notion, and you can do it your way as well. You take some notion of mean. This could be your weighted average of the people around you. You take some notion of count, like how heavily explored is this place already, and you can plug it into the very same formula to compute something that is called index, which is this combination of the average and the bonus, and then you can pick based on that index. So yes, something like that might work as well. My options were two options where you can use the decision tree or the fixed size neighborhood to populate these functions, but you can define these functions differently. You just need to make sure that they are like well defined, and generally it would work, right? So in this contextual bandit setting, you can do it that way. You can still use something like UCB formula, so it's very general, and like everybody basically is using something like this. Like they're often using some neural networks to estimate these values, like the counts and the averages. But this is the main idea behind all the advertising networks. Questions? If not, that's all I wanted to tell you about bandits. So we went through 3 very simple methods, how to balance the exploration and exploitation, but they are really the core of reinforcement learning. Every time you are learning something from feedback, you need to realize this trade-off between getting enough information, exploring, understanding the environment, and performing well. So these are already sufficient to do that. So all the big reinforcement learning techniques for Atari and so on are using these methods, like either epsilon greedy or optimistic initialization or something like UCB is already more in theory than in practice. But sometimes if you do research, then even in practice, we should understand them as well as possible. And large parts of reinforcement learning is just theory, understanding these basic concepts, and there are still some open problems. So if you go to a machine learning conference, there will still be like tens of papers about bandit problems, where they would have like different extensions, different assumptions on the distributions, how they work, like some very like not full satisfaction of the Markov property, or some other notions of regret, like that they don't want to just optimize the value, but they want to do something slightly different. So there still are open problems to solve in just the bandits. And it's our first like real reinforcement learning, algorithm learning just from feedback. And contextual bandits are very, very useful. Okay, we have 10 more minutes. So I'll just try to go back to MDPs. And in MDPs, you still can use the same principles, but instead of searching for the optimal action, as you are in the bandits, you are searching for an optimal policy. An optimal policy at time t is usually denoted by this pi t, and it maps states to actions. So every time in the MDP you are in some state, you have a probability distribution over actions that you might want to choose. In MDPs, you don't need to choose a random strategy. Like in games, you do have to play optimally, but in MDPs, it's always deterministic policy, which is optimal. So always the policy that would put the probability 1 to one action and 0 to all the others is enough. But very often in searching for the optimal policy, you are using these randomized policies, and that's why like reinforcement learning is full of randomized policies. Because if you already think about epsilon greedy, that's already like randomized policy, right? That's some kind of exploration. And reinforcement learning methods specify how agent changes its policy as a result of experience, right? So you are running episodes or continually running on the MDP, and you want to optimize reward in the long run. What does it mean? It's slightly more complicated in the continual settings. So after t time steps, you can have rewards t plus 1, t plus 2, t plus 3. But what do you maximize? Like you get a different reward in each step, and you can optimize different things. You can optimize total reward or average reward. Like if you optimize total reward, like sum of all the rewards you get over the episodes, the problem is that the episode can be infinitely long sometimes. Like if you are thinking about a problem like controlling an airplane in the air so that it's not shaking too much, that's something that you want to keep over a long time forever. You don't want to just sum it, because then the sum will go to like infinity. Then you want to have some notion of maybe average return or expected return. So people are actually, for different problems, optimizing slightly different notions of how you aggregate the rewards over time. The most common one is discounted reward, which is a discounted sum of rewards in time. You have seen it probably in the MVP definitions already, right? So you take the next reward with the full weight, then you have some kind of discount factor gamma, you take the next reward with just gamma of that, and the next one with gamma squared, the next one with gamma cubed. So you can have the discounted reward like that. What is the main distinction in reinforcement learning in these MDPs that I already touched on is whether the task is episodic or continuing. So the episodic tasks have some well-defined beginning and end. If you are playing a game of Go or something, you always start with an empty board, and you play the game of Go, right? And at the end, you win or lose. These are episodic tasks, or very in games it's like that. Or then the alternative are the continuing tasks. So if you think about some robots like living in some environments, some very complex, even self-driving car, right? You purchase the car and then you are using it for 20 years. And if you want it, not that you would actually, but if you wanted to adapt and learn from experience, like currently these things are not done online. So the cars are learning in simulators before they are deployed. They can be learning on hardware before they are deployed, but once they are deployed, they are frozen because you don't really want to a system you are selling to people to be adapting and changing in this security sensitive setting, right? So that's something that I wanted to mention at the beginning as well. Like all the success stories of reinforcement learning have been in simulation, either fully in simulation or mostly in simulation. So even the robotics cases first trained a lot in simulator. Like I think Tesla claims that the autopilot has like 10 times more experience, and now it will be even more in simulations than in real world settings, because something that is called sample efficiency, the reinforcement learning algorithms still are very sample inefficient. You need a huge amount of experience, way more experience that the humans need to learn anything, right? Like to a child, like child tries something 1, 2, 3 times and knows it for the rest of its life. These reinforcement learning algorithms, when they are playing like Go or learning to move with the robot, they have like millions and millions of experiences of a very similar phenomena, so that they can learn something. So they are super sample inefficient. That's why most of the success of reinforcement learning so far was either in simulation or on the internet with a scale of like millions of users looking at the ads, where you can get this data for a very simple problem and learn from there. But I was talking about episodic and continual tasks, right? So episodic tasks, beginning and end, and continual tasks are just going on for years and years, and you want to still be good and potentially improving in some settings on average. So continuing tasks don't have natural beginning and end of the episodes. But eventually it doesn't really matter too much. For continuing tasks, you can be very successful also with this discounted reward notion that I was just explaining. So the return, which is the term for the way how you aggregate the rewards. Like the reward is the thing that you immediately get, and the return is the aggregated rewards over some time. So if you have this discounted sum, then it has some nice properties. Again, from the stochastic approximation, this gamma is going down very quickly. So if the rewards are bounded, this discounted sum is always finite, right? So that's the nice thing about the discounted reward. So even if you have infinite kind of continual reinforcement learning problem that will happen forever, you still, for any policy, you can compute and define a specific value that this policy has, which is a number, which is finite, and you can optimize that number, right? And it's just weighting the immediate things more than the later things. It makes some intuitive sense, right? That you care more about the rewards you get now than the rewards you get into 20, 50 time steps in most cases, because who knows what will happen in 50 time steps, the world might end in the meanwhile. But it's mostly mathematically super convenient that once you have this discount factor, even if it's 90, like 0.99999, still if it's smaller, like strictly smaller than 1, then you have these nice mathematical properties that the sums are finite because it is exponentially decreasing still, and you can optimize it much more easily, and you can use it in all kind of convergence proofs and so on. So it's mainly for mathematical convenience, but it has also some practical implications. For some problems, you can see them both ways. You can see them both as continual and as episodic. Like one of the very fundamental problems is this pole balancing, which is just that you have this kind of card in one dimension, just to make it simple, and you want to balance the stick by just moving the car right and left, and you want to try to keep it standing, right? And that's a kind of a classical reinforcement learning problem. The angle of the pole is the state, and your actions are to move a little right or a little left to try to keep it up. And you can model it in different ways, like we were talking about modeling things as MDPs before. So you can give a reward +1 for every step that you don't fail. You can just give it -1 if it fails and give it 0 otherwise. There are implications of these different modeling decisions, like some of them are more suitable for some algorithms than the others. But what I want you to remember is this difference between episodic and continual task, right? So the way of giving it -1 upon failure would be the episodic. Yeah, I have it reversed here. But that would be the episode, right? Like you balance until you fall. That's the episodic view. if you balance and keep the rewards up, then it would be the continual view. But why it doesn't matter too much? Because you can transform it all, and usually the theory and the algorithms don't make that much difference about that, because always, if you have an episodic task, then you can assume that there is a loop at the end, which will just give you no reward forever, and you can assume that it's continual. And then you can have the discount factor of 1, which is like, it doesn't give you the nice mathematical properties, but it allows you to model things in the same framework. And the average rewards are used in some very special cases, but usually not, because it doesn't have the nice mathematical properties. Okay, and that's all I wanted to talk about. Next time we'll talk about actual solving of MDPs. So reinforcement learning is a set of methods to learn policy from an interaction with environment. The goal is to maximize some notion of return. That was this last bit that is somehow derived from the immediate rewards. It can be derived in different ways. The most common way is the discounted sum, but there are other options. The simplest reinforcement learning problem is the multi-armed bandit problem that is already demonstrating and allows us to study the exploration versus exploitation problem. We have seen 3 different algorithms to solve it: epsilon greedy, optimistic initialization, and UCB. And the canonical problem for other more complex RL problems are MDPs, and we'll be talking about those next time. Questions? Okay, if not, then thank you very much and see you next week.